Okay, so here is a problem that is a two-dimensional collision. We have a 1 kilogram ball moving at 1.2 meters per second collides with a stationary ball. So this is my 1 kilogram ball. It's moving at 1.2 meters per second. So I want to represent that as a momentum. So the vectors that are on our picture are momentum vectors. So I am going to have an arrow in that direction that represents the momentum of the first ball before collision. So that's ball 1. Now it says that it collides with a stationary ball of mass 1.5 kilograms. So that's why I made this ball a little bit bigger in size than that one. That's only 1 kilogram. This is 1.5 kilograms. So I made it look a little bit bigger. After the collision, now this is important. After the collision, the first ball moves off in a direction 48.2 degrees to the left of its original direction. So that means it has to hit and go that way. If it went to the right, it would hit and go that way. So when I say left and right, if I'm moving in this direction, up is left and down is right. So this needs to be put so that the first ball will move left. So I'm going to put it so that it's going to hit it above the equator. Because if it hits above the equator, then we can see that it's going to hit and go that way. And this one's going to, once it gets hit, it's going to go that way. Once I do it, I would check and double check just to make sure you don't have them going in the wrong direction. So it does say after the collision, the first ball, so the first ball moves off in a direction 48.2 degrees to the left of its original direction. So, and also look at the two angles here. Whichever one has the smaller the angle, the longer the vector. So I might, those are pretty close angles, but I might exaggerate this just to make it look that that's definitely bigger than that one. So, and notice also that both of these angles are with a reference to the original direction of the first ball. The original direction of the first ball we always make in the x direction so that all the momentum to begin with is in the x direction. So that means I'm going to extend that to the right. So I'm extending my x direction because that's part of my angle. So 48.2. Now, that's probably 40, 45, 40. So I'm going to go about right there. And what I just drew, that's going to be the momentum of the first ball after collision. Second ball is going to go. Now look, if I add those two angles, they're bigger than 90. So that's about a 90-degree angle. So that's going to be a little bit more. And watch how long I draw it. I draw it about that long. And the reason why I drew it that long is because I know that if I look at the distance, the vertical distance from the end of this vector to the x-axis should be the same as the end of that vector to the x-axis, because I know my two y components have to cancel out because there was no y momentum before collision, so there can be no y after. All the momentum has to be in the x direction. So if I actually add the x here with the x there, those two added together should equal that momentum. So this is the momentum of the second ball after collision. I should also put in the angles. So this angle right here is 48.2 degrees. And this is 51.0 degrees. And I used to have students also take this vector and break it into, like draw an arrow to there, which would be the x component of P1 after collision, and then draw an arrow up, which would be the y component of P1 after collision. Then draw an arrow here, which would be the x component of this one, and then draw an arrow there, which would be the y component. But the picture was too cluttered with all that, with all those arrows and all that labeling. So I think there's enough information just writing this that gives you a, so this is ball 2, that gives you enough information to solve for your 2 descriptive equations. What I have on the board right now is worth 4 points. So what I'm looking for is I'm looking for that the 3 vectors are on here, the 2 angles are on here, and the 3 vectors are all labeled. So that's how you get the 4 points. The next 2 points is to calculate the momentum before collision. So this is going to be, M1, V1. So M1 is 1 kilogram, and V1 is 1.2 meters per second. Hopefully most of you can do that in your head. That's going to be 1.2 kilogram meters per second. So right there, you're at 6 points. 4 points for the picture, 2 points for calculating the momentum of the first ball before collision. The next 6 points are just the descriptive equations. So I'm going to have, in the x direction, all the momentum to begin with was in the x direction. This is all in the x direction. So before collision, my momentum in the x direction is just P1. Now after collision, I only want the x components of my 2 vectors. So again, I'm going to show you, this is the adjacent side, that's the opposite side, that's the hypotenuse. For the other vector, that's the adjacent, that's the opposite, and that's the hypotenuse. So I want the adjacent components of these 2 vectors. Those will be my x components. So what should I write down? P1 prime times what trig function? Cosine of 48.2 degrees. And then it's going to be plus, because both of those vectors are to the right, it's going to be P2 prime times what? Cosine of 51 degrees. No, doesn't matter. Well, I'm just writing my descriptive equations right now. So in the y direction, before the collision, there was no momentum in the y direction. It was all in the x. So we know that before collision, it's 0. And then after, one of these momentums after is plus, and one of them is minus. If you look at this one, that's to the right and up, so that's your positive one. And this one is to the right and down, so that's your negative one. So I'm going to write first the positive, which is going to be a component of P1 prime. P1 prime times what? Sine of 48.2 degrees minus, because the other one is down, that's the minus. So minus P2 prime times what? Sine of 51. Any questions to here? Okay, now is just math. At this point, you have 12 out of 20 points. Now it's just math. You have 2 equations with 2 unknowns. I do know what this is, so that's not an unknown, even though it's a variable. But I don't know P1 prime, and I don't know P2 prime. 2 equations, 2 unknowns. I'm going to use the second equation to solve for either P2 prime, or P1 prime, and then plug it into the other equation. So I'll solve for P2 prime. So P2 prime, if I move this term to the other side, it would be positive. So I'd have P2 prime times the sine of 51 would equal this. So if I'm isolating P2 prime, it's going to be P1 prime sine of 48.2 degrees divided by the sine of 51 degrees. That is taking that second equation and just rearranging it to solve for P2 prime in terms of P1 prime. So now I can take this right here, and it doesn't matter which one you solve for. I mean, maybe half of you in here actually solve for P1 prime instead of P2 prime. You'll still get the same answers. So I'm going to take this, and I'm going to plug it right in there, because then I'll only have P1 prime in my equation, and I can always solve if there's only one variable, one unknown variable. So plugging in, I'm going to rewrite the first equation. P1 is going to equal P1 prime cosine of 48.2 degrees plus, and here is where I'm going to replace this with that. But I still going to have a cosine 51 at the end. So it's going to be P1 prime sine of 48.2 degrees divided by the sine of 51 degrees times the cosine of 51 degrees. So if you look at this equation, it's the same equation as the top. The only difference is this has been replaced with this. Everything else is the same. The cosine of 51 is still there. Cosine 48.2, P1 prime. So now, when an equation contains fractions, we multiply by the least common denominator. So least common denominator is this. So I'm going to multiply each term by that number, by that trig function. So that's one term, that's my second term, and that's my third term. When I multiply the third term by that, that's going to get rid of the denominator. So I'm going to have P1 times the sine of 51 degrees equals P1 prime cosine 48.2 degrees sine of 51 degrees plus P1 prime sine of 48.2 cosine of 51. So all I did was multiply every term by the least common denominator. Now, if you look, the unknown is P1 prime. P1 prime is there, and P1 prime is there. When the unknown is in more than one term, we factor it out. And what's going to be left in parentheses, that and that, I'm going to do two steps at once because I don't want to write all this junk down another time. So I'm going to move this down in the denominator, and I'll have it solved then for P1 prime. So P1 prime is going to equal this P1 sine of 51 degrees divided by all of this. So divided by the cosine of 48.2 degrees sine of 51 degrees plus sine of 48.2 degrees cosine of 51 degrees. Now, for those of you who have completed pre-calc or an advanced math class, then you would have learned trig identities. One trig identity is that the sine of x plus y equals sine x cosine y plus cosine x sine y. That is actually a trig identity. And if you look at the denominator here, this denominator is this. Because you've got the cosine of one of the angles times the sine of the other, plus the sine of the one times the other. So you've got the same thing as the trig identity. What that means is you can take this whole thing, erase the identity here, you can take the whole thing and replace it with the sine of, if I add those together, I get 99.2. So what I have here, right there, is actually equal to that, because sine of x plus y, if I add 48.2 and 51 together, it equals 99.2. This is a sine x cosine y plus a cosine x sine y. So you don't have to do that. You didn't even have to know the identity, but certainly you'd have to do more work, because you'd have to, punching this in your calculator, you'd have to make sure you use parentheses here and here in order to get the right answer. Yep. In fact, if you want to check it out. Do the two numbers and see if you get. Do it with all of this, and do it with that. Let's see if you get the same answer. So the P1 was 1.2, right?
Yeah. So you just get rid of the cosine altogether?
Well, I'm just saying that there's a trig identity that equals that. So I'm not getting rid of anything. I'm saying that there's an identity that equals that.
But if I were to do this on the test, I would just get rid of the cosine out of the sine.
What do you mean get rid of? You're not getting rid of anything. You're replacing it with.
Yes, I know.
So you get 0.945, right? .945 kilogram meters per second. If you put that in, you should have got 0.945. I can check. I'll check it after I go finish this. Okay. So now, once you know that number, the next three are easy. So that was the time-consuming thing to do that. Now all you have to do is go back up here and see where we have P2 prime equal P1 prime times that. We just solved for this, so now I just have to plug in that number that I just got, and I'll get P2 prime. So let's see if I can keep it there where I can see what I'm doing. So P2 prime is going to equal P1 prime times the sine of 48.2 degrees divided by the sine of 51 degrees. So plugging 0.945 kilogram meters per second. Now that number should be a little bit less than 0.945 because that's not a much bigger angle. 51 is not that much bigger than 48.2, so you're talking about maybe a little bit smaller, 0.9 something. 0.906. Now let's say on the test you get these two answers wrong. You don't get this answer right, and you don't get this answer right. Well, I'll still give you credit for the velocities if whatever you get for those two numbers, you divide by the appropriate mass. So once I know the two momentums, I can solve for the two velocities after collision because that's the other part of the question. What is the speed of each one after collision? So V1 prime is going to equal P1 prime divided by M1. So that's going to be 0.945 kilogram meters per second divided by M1 was 1 kilogram, right? So can do that in my head. 0.945 meters per second. So there's your velocity 1. Velocity 2 is going to be P2 prime divided by M2. So it's going to be 0.906 divided by 1.5 kilograms. And that's going to be what? 0.6 something? 1.5. What'd you say, 0.604?
Yeah.
All right, and that's the problem. So the last 8 points are right here. 2, 4, 6, 8. That's how this is a 20-point problem. It's more time-consuming than other problems, but